Math 1314 College Algebra topic, complex numbers, video 1, sets of numbers you may already know. Apologies up front. I forgot to bring my headset with a microphone on it. And so the room I'm recording in right now does have a slight echo. In future videos, the echo should not be an issue because I won't be in this room and I'll have a microphone right here. All right, so let's begin. Now, if you're going to watch this complete series of videos all the way from here until, well, the end, then you're going to see a lot of things that you may know and some things that you may not know. But my goal in these videos is to present all of the topics necessary for a general college algebra class in bite-sized chunks. My goal is to try to keep most videos around the 10-minute mark. And I hate saying that up front because I know that at some point in the future, that's not going to happen. But I will have a timer here so I can keep an eye on it. Okay, so if we're going to be doing algebra, which is basically math with values that you don't know, which is why we have variables, then we should probably talk about the values that we do know first. In other words, numbers. Now, everybody's familiar with numbers, and a lot of people have the misconception that math is just about numbers. That's kind of like saying that literature is just about the alphabet. Numbers are a tool that we use to solve some problems in math, but they're not the only tools. However, it would be good to have a familiarity with some specific sets of numbers. So we're going to take these from smallest sets to largest sets, starting with the natural numbers, which are also known as the counting numbers. They're the set of numbers that you count with. If I ask you to count, you're going to go 1, 2, 3, 4, et cetera, et cetera, et cetera. Now, a little bit about the notation here, starting with, one second, getting this ready to go. Starting with these 3 dots. I'm assuming that you've seen these dots before. In grammar, they're called ellipses, E-L-L-I-P-S-I-S, and they indicate that you have a pattern or a list that continues as defined by its first members. In this case, saying 1, 2, 3, and so on, pretty sure everybody would pick up on the pattern and know that the next elements in this set are 4, 5, 6, 7, and so on. The other notation I wanted to point out real quick are these braces. In math, whenever you have a collection of objects, a set, if you will, they're often enclosed in a set of braces. So all those braces do is serve as a grouping symbol, saying that we're looking at these as a single collection of objects. Each of the objects are called elements. So we could say something like 1 is an element of the natural numbers, or we could say something like 0 is not an element of the natural numbers because it's not inside of that list. Now, for the longest time, these were the only numbers that we needed. But the advancement of math bounced back and forth between what can we do versus what can't we do with the current things at our disposal. In this case, if we only had natural numbers, there are several algebra problems we could solve. For example, we could solve something like x plus 5 is equal to 6. Now, it should be fairly obvious the solution to this is 1. Because 1 plus 5 is equal to 6, I made an equation involving natural numbers and its solution was a natural number. However, if these are the only numbers you know, then you could not solve this equation. X plus 5 is equal to 5. Now, we all know what the solution is, or at least we should. What do you add to 5 to get 5? The answer is 0. But if the only numbers you know are the natural numbers, then the number 0 does not exist. And so one of two things happens. Either we've reached the end of math or we need some more numbers. Well, this is going to be a recurring theme throughout this video. We need more numbers. Of course, the solution to this is 0. So we're going to make a larger set of numbers by including 0 up front. And that set of numbers is called the whole numbers. Now, there's a few ways to remember that the whole numbers include the number 0, whereas the natural numbers do not include the number 0. I'll admit, when I first learned these, I had trouble remembering which was which. But the easiest gimmick is to remember that the word whole contains an O, which kind of looks like the number 0. So the whole numbers include the number 0. And this fixes the problem we had before. Previously, we had an equation like x plus 5 is equal to 5, which is made up of whole numbers. It's also made up of natural numbers. As a natural number equation, it has no solutions, but as a whole number equation, it does have a solution, x equals 0. All right, so we fixed that problem. We fixed the problem of this red equation not having a solution. We needed more numbers. All right, problem solved. But can we make more numbers? Can we make another equation out of whole numbers that does not have a solution if all we know are whole numbers? And the answer is yes. For example, if we had something like x plus 6 is equal to 5. There's no solution if these are the only numbers that you know. Now, we know what the solution is. You probably do, because you would probably remember things like, if I subtract 6 from both sides, blah, 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 and I end up getting x equals -1. But if these are the only numbers you know, then there is no such thing as -1. And so again, the development of math kind of reached an impasse. Have we reached the end, or do we need more numbers? And the answer, of course, is we picked up more numbers. And the numbers we picked up are the negative numbers. Now, the negative numbers are less than 0, so we have to write them before the number 0. And when we pick up the negative numbers, we get what's called the integers. Notice that this does have ellipses up front and at the end, because the integers go infinitely in both positive and negative directions. So we have to start this with an ellipses, jump in on the negatives, cross over to the positives, and then conclude it with an ellipses. And this seems like we fixed everything, because now an equation like x plus 6 is equal to 5 does have a solution. Its solution is -1. And if you're worried about me taking that for granted, and not saying, well, aren't you supposed to subtract 6 from both sides and cancel and write x equals -1? Yeah, but some of the small moves I'll take for granted. Right now, we're just discussing sets of numbers. But let's see if we can break the math again. In other words, can we come up with an equation that uses integers whose solution does not exist in integers? And the answer is yes, but you have to step away from adding and subtracting. For example, if I gave you something like 2 times x is equal to 1. Now, having seen algebra before, I mean, you should have, you probably know that the correct move is to divide both sides by 2. That would cancel the 2's, leave the x by itself. But now the problem is, what is this thing? This thing does not exist if the only thing that we know are integers. And you're probably thinking, great, here come the fractions. Life was better when I didn't know about them. But the truth is, fractions are predictable. You shouldn't be scared of them. When the time is right, we'll discuss all the rules for adding, subtracting, multiplying, and dividing, but they're not really that bad. They are predictable. And we ran into an impasse again, because again, the solution to this is not in the set of integers. So we need a larger set of numbers. And this is where the fractions and decimals come in. Now, there's a problem here, because if you notice, what I've been doing is taking the previous sets, starting with the natural numbers, and putting more numbers into them. We start with 1, 2, and 3, then we throw in the 0, then we throw in the negatives. Now we're going to pick up the fractions, but the problem is, how are we going to write them? Are we just going to write them all in order? For example, where would 1/2 go? Well, it would go between 0 and 1. Well, if we wrote this, did we leave any fractions out? Are there fractions that live here? Are there fractions that live here? And the answer is not only yes, but there's an infinite number of them. There's a property of fractions called density that basically says, if you give me any 2 numbers, I can always find another one in the middle. And then in the middle of those, and then in the middle of those. So they're too densely packed in for me to list. So if I can't list all the fractions, how am I going to write the next set of numbers? Well, we're going to describe them using something called set builder notation. The set of fractions is called the rational numbers. And the reason it's called the rational numbers is because a fraction is really just a ratio of 2 numbers, one on top of another. Allow me to elaborate what all these symbols mean. It's really not nearly as bad as it seems. In fact, I'm going to type how you would read this. You would read this expression on the right side of the equal sign as the set of A over B's, so plural, such that A and B are elements of the natural numbers, I didn't say this earlier, but a capital N, when talking about sets of numbers, refers to the natural numbers, such that A and B are elements of the natural numbers, and B is not equal to 0. I'm horrible at typing. We'll see that throughout this series of videos. So it's a lot of words to say just for this one. I'm going to kind of highlight different pieces and the words that they translate into. For example, when I say the set of, that's basically announcing that I'm opening a set. Now the A's over B's, that's just describing the things in this set. Let me make that a little bit wider. The set of A over B's, that vertical line after the fraction is translated, let me turn my phone down, is translated as the phrase such that, and then there's the A and the B. We'll put that in purple. I hope I don't run out of colors. But that, let's do this one. This funny looking symbol here is the symbol for the phrase is an element of, but in this case it's plural. And then the capital N is the symbol for the set of natural numbers. And of course, the rest of it, which I'll just highlight in a red box, B is not equal to 0, is this part. So it's a real fancy symbolic way of just saying all those words. The rational numbers, the fractions, are the set of all ratios of natural numbers. And honestly, it shouldn't even say natural numbers, it should say integers. So give me 1 second to fix that. And I realized I've already passed the 10-minute mark. Fixed. And believe it or not, the letter for the integers is a capital Z. It's for the German word for integers. The rational numbers are the set of all fractions such that both sides are integers. So put an integer on top of an integer, except the bottom can't be 0. Great, so we pick up all the fractions, and is that all the numbers? And the answer is not quite. Why not? Well, here's why. There's another way to think about the rational numbers. If you were to view them not as fractions, but as decimals. Now, you probably know the decimal equivalents for some fractions. For example, 1/2 is 0.5. Or you may know other fractions such as 1/3. 1/3 is 0.3 repeating. Recall that when you put a bar over a number after a decimal, it means that that value or values repeat indefinitely. And something that not everybody knows is the following. Every rational number, as a decimal, every rational number as a decimal either terminates like 1/2 or repeats like 1/3. And you might think, okay, so what's the big deal? Well, there are decimals that do neither. In other words, there are decimals that don't end like 1/2 and don't repeat like 1/3. What's an example of a decimal that doesn't do that, or that does neither? Pi. Now, most people think pi is 3.14, but the truth is it's 3.14159, and then it goes forever and never repeats. So if it goes forever and never repeats, then it can't be a rational number, because as a rational number, it would either stop like 1/2 or repeat like 1/3. So what do we do with numbers like those? Well, we need a bigger set of numbers. So if you think of the rational numbers as the clean decimals, the well-behaved decimals, decimals that either stop or repeat, then we're missing all the decimals that don't behave well, the decimals that go forever and never repeat. They're just a random collection of values. Well, not necessarily random, but they're a set of decimals that go on forever and never have any discernible repeating pattern. So we're missing those types of decimals. Well, if we throw those in and have every single decimal that you could possibly have, then we get something called the real numbers, the set of all possible decimals. And this includes every number that you've probably ever seen before, except we run into a problem. And I did kind of diverge from the path I was taking, where we would set up an equation that fails to have a solution. Such an equation over here would be something like x squared is equal to 2, which if you square root both sides, you get the square root of 2. But the square root of 2 is not a rational number. So it's not in that list. But when we get to the real numbers, all the possible decimals that you could have, it seems like that every equation that we can make would have a solution, except it doesn't. And here's why. If I make the equation x squared is equal to 1, what would it, I'm sorry, that would have a solution not only of 1, but -1. But x squared equal to -1, what could its solution be? Well, think about all the real numbers, and the easiest way to think about them is to think about a number line with 0 in the number in the middle, positives on the left, on the right, negatives on the left. Sorry, my brain's at about 5 places right now. What number could we grab off of that number line, square it, and get -1? Well, we couldn't pick a number over here because when you take a positive number times a positive number, it's positive. We couldn't take a number over here because when you take a negative number and square it, multiply by itself, negative times negative is positive. And clearly 0 doesn't work either. 0 squared is not -1. So does this have a solution? And the answer is the solution to this equation is not a real number. So what is it, and where does it live, and what type of number does that create? Well, that's what we'll talk about in the next video. And I feel bad that my very first video didn't even meet the 10-minute criteria. I will try better on subsequent videos.